Al Williams here. A while back in Hackaday, I was writing about bit-sliced processors, and in particular the AM2900 from AMD, the 2900 family. And just on a lark, I decided to go look on eBay and see if I could find anything to buy for that particular, I was thinking chips or who knows what. And it turns out I found this pretty much mint condition AM2900 evaluation and learning system, and it's really in great shape. I managed to mess up one of the switches, but it's working pretty well, so we're going to see how it goes. And it lets you kind of experiment with that technology. So it wouldn't be fair to say this is a 4-bit CPU because it's really only part of a 4-bit CPU, but the idea behind BitSlice is it could be expanded. So you could have used multiple of these chips to make like an 8-bit processor with 2 or a 16-bit processor with 4. And these were in a lot of mini computers and workstations and all sorts of other things. They were also in some video games. So kind of an interesting technology. It was kind of the bridge between building a computer out of just pieces and having a whole computer on a chip. It was kind of like, well, these are these building block chips you can use to do a computer. We'll look at the schematic for this, and I'll show you a little bit more about how it works internally. But for right now, I just wanted to give you a quick tour. Like I mentioned, this is the ALU. This is where all the logic happens. There's some registers in there, 4-bit registers, of course. And this large chip over here, relatively large, is the controller. And it actually controls which piece of microcode this is going to run next. So say this was part of a larger mini computer, the user would have some 16-bit instruction, probably, or whatever bit number it was, and that would get mapped into this microcode, which is actually living on this memory right here. It's 32 bits wide, and one instruction might map to a sequence of microcode. So each one of these bits in the microcode will say, put this register on the bus, or read this register from the bus, or go to this next address later, or turn on the status latch, or whatever. And so a particular instruction might have one micro instruction that says, put these things on the bus, load the ALU with this function code. Then the next step might be, okay, now go read the ALU output and put it somewhere. And then the next step would be, probably in a real computer, go read the next instruction and start all over again. So that was a very common way to do CPU design back in those days. The board itself takes a clock, although if you keep it in single step mode, you can use this switch right here to do the single step. There's, again, 32 bits of microcode storage. There's a 32-bit pipeline register. So there's only 16 microcode instructions that this board can hold. So 16 32-bit words are in this RAM. And then when you load one of them, it goes into the pipeline register, which then is what the rest of the board is processing for that cycle. You might wonder, if it's a 32-bit microcode, why are there only groups of 4 LEDs? Keep in mind, all the data path is 4 bits. But the microcode is 32 bits. Well, there's a trick to that. If you look, these are data LEDs, and they show different things. I'll show you how to know what it's showing in a minute. This is the pipeline register. That's the current instruction. And this is actually the memory address. Memory contents, the micro program contents. Now, it's 32 bits, and so is the pipeline register. So how is it able to show 32 bits and 4 bits? Well, the answer is these 3 switches here. So it breaks the word up into 8 words from 0 to 7. So right now, we're looking at byte, or nibble, I guess, 0 of word 0, because this is the addresses. So if I want to look through that word, I would have to go, well, that's nibble 1, nibble 2, nibble 3, nibble 4, and so on, until you could get all the way to 7. You'll notice the data display is changing too. This bank of switches not only controls this LED and this LED to walk through the memory arrays, but it shows different things. So like right now, if I'm not mistaken, it's showing the next address from the controller. but with the 1, it's showing the output from that chip, and it shows different things depending on which of the 8 settings you have it on, and they're not related. It's not like, oh, this is the top part and this is the bottom part. It's just 8 different data values that show up there. And then these switches control the data going into the microprogram RAM. So you can run or you can load. Right now we're in load, and that means we won't really be using this switch. And I'm going to show you later how I put together this sheet, but this is a little 16 microcode instruction set to take 2 BCD nibbles and convert them into an 8-bit binary number. Keep in mind, there's only 16 instructions, so this pretty much fills up the entire board. It's pretty funny. I'm not going to show you every bit of this because it's very tedious, but I wanted to give you a flavor for how it works. So right now we're at address 0 and byte nibble 0. I say byte, but it's really nibble 0, and we need to put 6 in there, 0110. So we're going to push this button, and you'll see that in fact the LED that shows what's in the memory changed to 6. So I'm going to go to 1. We need 0 in there. This particular cell is blank, so we don't care about number 2, but we do care about number 3, which needs 3 in it. Okay, and then 4 needs 7 in it. And all these have different things that it makes the, 7 might mean store this in such and such a register or whatever. And in fact, what we're doing here is we're ORing a constant, which was 6, that first 6 that I put in, with 0, and storing it in register 0. So going over to 5, we need a 3 and 5. And again, it's a good idea to make sure it's really showing up on the LEDs that way so you're not making any mistakes. And then on 6, we need 2. That 2 is what tells this chip to go on to the next instruction and don't try to jump anywhere under any circumstances. You would think it might be useful to say, okay, now I'm going to go to address 1 and I'll just reset all this and start over from right to left. But in fact, I find it easier to go down and back over and then down and back over and just kind of zigzag through the paperwork here. So we already need 2 again, because again, that's telling it to just go to the next instruction. So we're going to put that in, and now we're going to go to 5, where we need 3. Now keep in mind, we're in address 1 here. You can see that. Okay, so we're putting 3 in there. 4 needs a 7. 3 needs a 3 again. 1 needs a 1 because that's register 1 is what we're going to load into. And the constant that's getting loaded in number 0 is going to be 7. And so this is those 2 lines represent the BCD digits 7, 6. We put 7 in R1 and we put 6 in R0. Obviously you could change that if you wanted to try a different problem, but that's just what I started with. So I'm going to do one more row, and then I'm going to quit talking and we'll speed up through that, or I'll cut it off and I'll come back when it's done. But again, I'm going to start now at the bottom, and at line 2 I need 0 at 0. So we're going to set the switches to 0, and there we go. And this one's a little easier. The next address I've got to set is 3, and as usual, it needs a 3 in it. 4 needs a 7 in it again. And 5 this time needs a 0 in it. And we'll see what all that means in a little bit. And then 6, again, needs the 20 to go to the next instruction. Sometimes there's other things it needs to do, but that it's not uncommon to see a 20 in that field, or I'm sorry, a 20, a 2 out of 20, I'm thinking hex. So 0010, which is 2 in that field. So I'm going to go on and go back and do the rest of these. That line, by the way, just for out of curiosity, put a 0 in the Q register in this chip, which is more or less like an accumulator. Now keep in mind, right now, none of those things are happening, right? We did not load anything in register 0, register 1, or register Q. What we did is we put instructions in this memory that when we run, it's going to make those things happen. So I'm going to be quiet now, and I'm going to go on to line 3. I wanted to look a little more at the schematics for the board we were just looking at. So you can see these schematics, by the way, were scanned by somebody on the internet, although there's a nice copy in the book that came with the board, and there's a couple other sources for them. But I took that scan, made a few notes on it, and also just kind of color coded it. So the biggest thing here on this page is the microprogram memory, which that's the 32 bits by 16 microprogram words. And that's controlled by the sequencer. That was that sort of larger chip down towards the bottom of the board. When it's loaded, when a particular instruction is loaded, it goes into the pipeline register. And reality is that pipeline register is actually in the 2900s. This particular piece that says pipeline register display is purely to allow the LEDs to show what's in the pipeline register. So it's really a copy of the pipeline register that drives these LEDs. And you can see the data switches here go right into the memory. Here's the mux switches, those 3 switches to the far right. And you can see there's 2 different places they're decoded into 8 lines. One is always, and one's just when they're being in the load mode. That load run setup goes through here. That controls several things if you're in load mode to keep the sequencer from doing anything bizarre. And when you're in regular run mode, it kind of passes through everything from this next address prom. That next address prom is the socketed part. And so it's taking a couple of bits from the pipeline register and saying, okay, you know, you should push your stack or not push your stack or read the next instruction or jump to this particular instruction. So that's all controlled through that prom. This is just display stuff here for the memory. And that's kind of it for this page. There's, you know, some power supply filtering, stuff like that. Down at the bottom here, though, we've got, let me get that where you can see it. We've got a couple of things going on. Here's the ALU, and I mentioned about how the shift register, or shifting things in the registers is weird. It's because the carry comes out, meaning it should go to the next ALU, but in fact, we mostly want it to wrap around. So there's these muxes here, and where are they controlled from? You got it, the microprogram memory. So during a shift instruction, you can control these muxes to say, yeah, I want you to just put a 0 in where you're shifting bits in, or I want you to take the output and shift it back into the input, or vice versa. So all that's controlled there. The ALU generates a status register contents, which is like carry, whether or not it's a signed bit, if there was an arithmetic overflow, I think there's one other, and all that gets latched here. And then more bits from the instruction go through and say, hey, is this a conditional? If it's a conditional, I'll pick which condition it is. It's 0, so that'll come out on this CCE line, or it's overflow, so then now the overflow will come out on that CCE line. And the significance of that is if you go back to the sequencer, that winds up going into that prom. And so based on some of these things that come into the prom say, hey, don't only jump if it's a 0. Well, that's, there's bits that will tell it the CCB is 0. And then, so then there's the clock. That's just purely a single step clock when you push the button, or an external clock. And this is the data display. You can see there's 8 very different things that go on based on that, and I'll cover that here in a second too. There's one little strange thing on the schematic that I'm really interested in, if anybody knows what it's for. There is a bus transceiver U35 down here. It's connected to the output of the ALU. If you notice, the output enable, the chip enable, and all those things are asserted constantly.
So the way this works is supposedly there's open collector outputs on the bus, and then there's non-open collector outputs here, and it does calculate parity. As far as I can tell, none of this is used, and even more bizarrely, whatever you put here comes out here and here, and the only place these are all three used, well, I take that back. This is used in different places, but the only place this is all used is in fact at the display. So on certain bit patterns of the mux, it will say, oh, I'll show you the bus, or I'll show you this, but it's always the same. The only thing I can figure is there's three little things that look like they might be jumpers in the schematic. I don't see them on the board, whether they're just traces to cut or if were meant to be jumpers there and there's not. But my guess is this was meant for some future expansion that never happened, that they were going to make something that, you would cut these jumpers, wire something into it, and then more things would hook up, or maybe you could hook two boards together, or I don't know. But there seems to be no real reason for this to be here. A fancy bus transceiver that's wired to just pass everything from here to here to here and goes essentially nowhere except the displays. So anyway, that's that. And the only other thing I'll do is take you through the manual and we'll reconvene for that. Okay, very quickly, I wanted to kind of go over some of the manual for the board. It'll make some of it make more sense. This is actually what the 32 bits of microprogram memory look like. So when the switches are at 0, you've got those 4 bits there. That's the D bits, and those are just data bits. So if you want to load 1 into something, or 8 into something, this is where that goes. Then there's the A and the B, and the A and the B are actually register addresses. There's 16 4-bit registers inside the ALU, and you can name them here by using numbers from 0 to F hex. So why are there 2? Well, you might want to say A plus B, for example. And the trick is it can read from A and it can read from B, and we'll see how that works in a minute, but it can only write to B. So you can never write to A, you write to B. And you don't always use A and B, and we'll look at that in a second. The next thing is an ALU code. I'll show you those in a minute. And the carry bit, which, as mentioned, you got to hardwire it to 0 or 1. That's the carry input. You can't say, oh, I want the carry from the last operation. It would have been possible to do that, but the board designer didn't allow for it. Then you've got a source select and a destination control. This is going to tell you what you are reading, and this is going to tell you what you are writing. And these 2 mux bits control the shift register mux. So all this has to do with the calculations. The 6 and 7 fields are the next instruction control and the branch address. So this is where we were putting those 2s all the time that said go on to the next instruction. But then sometimes you don't put a 2 there. And in fact, if you look here, this is what all of them are. You can do a 1, which is just a hard branch, or you can do a 2, which is a continue, or you can do a branch conditionally if the result of the ALU is 0. The things that have to do with file reference, that's like the top of the stack. So there's actually a small stack in here so that you can do things like jump to subroutine, do a couple of lines, and then go back, do a return basically. And you can also do things like, no, I just want to get rid of it and pop the stack and keep going. And then you can see there's different conditions here for branching as well. So it's fairly limited. There's only a few things, and like sometimes you really want to branch if the carry is not set. Well, too bad, because you can only branch if the carry is set or some other condition. The other thing that's interesting, because of the pipeline register, this really applies one off, right? So when you load the pipeline register, that bits that are here in field 6, they're going to apply to the next instruction you fetch. So, but they're going to use the conditions that are from the previous instruction. So in other words, if I have instruction A that does an add, let's say, and I want to jump if that add produced a carry, I have to put this on the next line for instruction B, and then it's going to execute instruction B, and then instruction C will come from where the branch destination was. So it's a little bit to get used to because you do have that delay. The data you're working with is what makes the next instruction load up, but you've already loaded the next instruction. So it's a classic pipeline. It's just one deep. Now, we glossed over quite a few of those, and they gave you this nice handy reference, and there's only one problem with it. The reference, let me find it here. Yeah, here's the reference. They say, oh, this is a handy reference when you're programming. You can use it. It's the programming guide. And so I want to go back to the, we'll skip the first part of it. I'll show you that in a second. But you can see here's the ALU function select. You can add R and S. And what's R and S? Well, we'll get to that. You can subtract R from S. You can subtract S from R. You can do OR and, not R and S. You can do an exclusive OR or an exclusive NOR. Notice that none of these things do copies, and I'll tell you about that in a second. But the S and R come from this thing, the source code. You remember there was a 3-bit source code. So depending on what that is, you can say, well, I do want A and B, that's one. Or I want A in the Q register. The Q register is like an extra register that's an accumulator. Or I want 0 in Q, or 0 in B, 0 in A, or I want the D. Remember the D field in the instruction? I want D in A, D in Q, or D in 0. So my source control says pick these things for R and S. Here's what you do with R and S. And then, oddly enough, the destination select tells you where are you going to put the result. Well, I'm going to put it in Q. I'm going to throw it away. I'm going to put it into RAM, meaning I'm putting it into the B register is what that means. Or I can do some shifts and some double shifts, and I'll actually use that in the program that I put in. And that depends on what you want to do for shifting, whether or not you want to divide by 2 or multiply by 2. It's still just a one-place shift. Now, how can you do, like if I wanted to move A to B, how can I do that? Well, I can say, let's pick my R and S to be A and B. I'm sorry, 0 and A. And then I can say, let's do R or S. Well, with a 0 in it, it's going to be the right, it's going to be the same thing. And then my destination control can write it to B. So that would let me copy A to B, for example. There's a lot of little quirky things like that you have to get used to. The MUX control tells you how to do shifts. That's only really meaningful if you're doing one of these shifts. And it basically tells you, are you going to shift zeros in? Are you going to rotate around? Or are you going to do a double length rotate between F and Q? And we'll actually use that in the program. So pretty interesting. Now, here's the problem. The manual that I have, this is a scanned manual and it's apparently pretty old. The manual I have has a much cleaner, nicer, professional looking table than this, a little easier to read. You can see some of this is pretty scrunchy. But what's worse is this is just completely wrong. Do you remember we looked at the table earlier and it had all the different branches? Well, 2 was a continue. Well, not on this table. It's a push, and branch is a 0, which is not right either. So this is just completely not the case. And in fact, some of the examples in this scanned menu are wrong, although in a different way. So there were at least 2 mistakes I found, and I was thinking, well, maybe I just don't understand what's going on. But when I got my kit and it had an actual later manual with it, all these mistakes had been fixed. So I'm pretty sure they were really mistakes and not just something else. So that's kind of the part of the manual that's more interesting. You actually had to build this, I think, in some cases. So there's all this assembly, kind of almost Heathkit level assembly instructions for it. It doesn't look like mine was something somebody assembled, or else they did a really nice job of it, but it also didn't look like it had come in any different way. It was nicely bagged with anti-static foam to cut for it and everything. And they also gave me a bunch of these nice sheets, which I scanned, and I'll make an available copy of the scan, where you can go write all your ones and zeros using that table to get the different instructions. Here's the thing. I don't use this, and I'll show you what I do use next. Great. I wanted to show you how I wrote the little BCD conversion microcode program. I could have used the little paper tables and the paper uh, forms and filled out all the ones and zeros, but I decided I didn't really want to do that. And so I, of course, foolishly made a assembler, if you will, in Google Sheets. And so at first I just had numbers, but I've actually since changed it to do labels. And you can, in fact, still use the numbers. So if you don't like using the labels, no problem. But you can see this first column are labels. They have to start with a colon. You have to make some concession to the fact that these are spreadsheets. And there's exactly 16 of these rows, one for each memory cell. And you come in, and if you say, well, I want to do a branch, then it tells you where do you want to branch to, 0 to F. But you can also put in a label. So like this is a branch to here. It says it's invalid, but that's only because it's not 0 through F. But it's smart enough to know that if it's a colon, it's got to go look it up, and that's going to resolve to E. Then you wind up with the next. So normally that's going to be continue, but it can be other things. The MUX for the status registers, and the destination control, and the source, and the carry, and the ALU code. And all of these will show you all your choices when you fly them out. And then there's A, B, and the D. Now, you could put numbers in here, like here, I've got 0, and that's fine. Or you can put symbolic names that start with exclamation points for these registers, or the octothorpe #, hash pound, whatever you want to call it, for data. Keep in mind the data is 4 bits. And so if you look below the black line, there's names for registers. And because you might want to call registers different, there's also this kind of free-form area where you can put aliases. So for example, bang res 0 is the low result nibble, but it's also the MSD, IMSD. And so the reason for that is you don't have a lot of registers. If you were really going to do something serious, which you're not in 16 lines, but if you were, you might want to reuse some of these registers, and this prevents you from just having to have a generic name. The constants, here's the inputs. I told you we had 7 and 6. And then this is just a little reference to remind you what the MUX field means. I didn't want to make this even wider. This does look better on a wider screen, but for the video capture, I'm on a pretty narrow screen. So then here's all the output, and all this is automatically generated, and you get a warning if you try to change any of it. So this is what you've got to go type into the keys. And then this is just a little comment field. What's interesting is this is too much to look at when you're trying to type all that in. So if you run a macro, it will hide everything except that. And that's the printout you saw me working with in the videos, is it just shows you the address, the bit fields, and I left the comments in just so you have some idea what you were looking at. And then another keystroke will bring it all back out so that you can modify it. This is much more sane. And so I'll let you work through it yourself, but just looking at the comments, it's kind of what I described before: load 6, load 7, put 0 into Q. Q and R1 are going to equal to 2 times R1. We're going to save that away in R3 and R4, multiply by 4, multiply by 8, add them all together. If there's a carry, we're going to jump down here, and you might say, oh, you could have done the R2 for carry and come back around for, only used one instruction. The problem is they have to go back different places, and you say, aha, but they had to jump to subroutine. But the problem is I can't jump to subroutine when there's a carry. So I would have had to use more instructions, and I don't have any more instructions. So I would have had to say, okay, jump to where I call this subroutine or not based on the carry, and then call the subroutine. It was much easier to just put the one line that does the carry addition and then jumps back to where it's supposed to go. So that's something to look for if you're trying to wade through this. The other thing that's interesting about it is when you do these carry calculations, like I said before, the instruction you're on, it's really looking at the carry from the previous instruction. So you can see here, after we add in that least significant. I got least significant byte there, but really it's least significant nibble or digit. Once you add that in, you need to handle the carry. You don't really need to do anything else, so everything else is kind of not handled, right? And that's fine. But you can't say, I'm going to do it on this line, because that's going to load the next instruction before we know what the result of the addition is that may have generated the carry. So again, pipelines are always fun. At least this one's only one level of pipeline. And I think with that, you've got pretty much everything you need to know to go through and do something like this. My plans, which may or may not materialize, and I'll certainly mention on Hackaday if they do, is I'd like to make a actual emulator in this spreadsheet so that not only could you write all this like this, but it would copy these bit patterns over and then interpret them in the spreadsheet. We'll see if I get that far or not, but it's just a great brush into history. A lot of really famous machines worked like this internally. Everything from the Xerox Star to the Apollo workstations, which is not the Apollo astronauts, it's Apollo, the company that competed with Sun for workstations. HP 1000s, some of the DEC computers use these internally, and it was just the way you built oddball computers when you couldn't get it all done on one chip. So anyway, that's how it all works.
Okay, well, of course, every time you power off the board, you lose everything. So I'm hoping I got it all in correctly. We'll see. I'm going to set the address back to 0. And in fact, I think I'm just going to 0 all the switches for fun. And I'm going to go ahead and hit the single step. And what you'll see is that didn't clock it, but it did load the instruction register, or the microprogram register, or excuse me, the microprogram cell at 0 into the pipeline register. So if you notice, if I start tracking this, they'll track exactly because they've got the same contents in them for now. And then I'm going to switch over to run. And what you'll see is when I hit the single step, right now that data display is at 0 and it's showing me the microcode address that's executing. But every time I press the button, and I could see things like the result of the ALU, which at this point doesn't mean anything to us because we're not looking at the code. But what you're going to see is eventually it's going to converge on C, D, C, D. And so that's going to tell me the values when I look at the ALU, because the instructions there are just to display register 0, display register 1, and go do it some more. So if you'll notice, we've got a C and a 4 in there, and in fact that's the right answer. So 4C is in fact 76, and that's the numbers that we put in at the beginning. And I'm just going to let you take my word for it. If we put different words in it, it would have come out to the right answer.